Hi, I want to show you some things about the magnetic field, geomagnetic field, and also induced or remnant magnetic field in some of the commercial magnets we can find in stores. Let me first introduce you the sensor. Okay, here we have, if you take it out of its base, we have a small, compact, very sensitive fluxgate magnetometer. Okay, there's a toroidal coil here with a 2000 turns primary winding and a secondary winding that is wrapped up around the toroidal shape, as I explained in the class. So this sensor is controlled by the electronics on this part of this board. So we have a 25 kilohertz in excitation signal, and then we have electronic that basically filters, detects the second harmonic, integrates the signal, and then calculates a value that can change over time. So I can show you something without any objects, magnetic objects around. We can basically move the sensor, just rotate it in the vertical direction, okay? And you can see that the signal changes. You can see the plot here on the screen as well, with the reading in volts, both in the tester and the USB connection that reads the data from the electronics. So if you move it around, this yellow bar on top of the flux gate sensor tells you the direction of sensitivity. Okay, so whatever field is moving in this direction is going to provide a positive reading. If we flip it over and we put it exactly in the opposite direction, you're going to have the same amplitude but change in sign type of voltage. So what I'm gonna do is, instead of working with a geomagnetic field, that's what we're doing right now. Okay, we're showing you that the magnetic field varies in amplitude and depending upon what is the orientation of the sensor with respect to the geomagnetic field. So what we're gonna do is, since we cannot change the field coming from the Earth, and we cannot change the any disturbance produced by metals in the table, or some bolts and some metallic components on the laptop computer and such. What we're gonna do is leave the sensor fixed, which basically give us like a constant background. You can see now that the readings stabilize at about 0.65 volts, and whatever we move around that have some intrinsic or remnant magnetization, like a magnet, is going to produce its own anomaly superposed to that DC background. Okay, so what I have here is a set of different magnets. Okay, you have some magnets here you can buy, in any store. Have several applications. These magnets, as have some magnetization that is parallel to the axis of the disc of the puck. We're gonna use two. Okay, we're attaching one after the other, and we're gonna place it on a movable platform. In other words, if I place it in this platform, okay, and I slide the magnet below the sensor, we can kind of assume, as long as I keep the magnet moving at a uniform speed, what we're gonna see on the screen is pretty much the anomaly produced by the magnet. So let's start before the screen switches to a new set of numbers. So you see, as I move the magnet right under the sensor, the voltage produced by the flux gate is going to change, and the resulting shape of the voltage as a function of the position can be seen on the computer screen. So you can see that we have now a full anomaly. So we're going to do back, now that we are starting a new graph string, we're moving the magnet back, and you're going to see how the anomaly gets assembled once again. So this is the magnetic anomaly of the magnet. Let's say we flip the magnet now. Okay, you see that the change was detected by the fluxgate, and we start again the measurement. So we approach the magnet to the position of the fluxgate sensor, and you're gonna see how the amplitude, now with the opposite sign, now it looks positive, is drawn on the computer screen. If I accelerate or decelerate the magnet, obviously the shape of the anomaly is going to change. So this is a little bit sharper than this one, but certainly has the same amplitude and pretty much the same width. Now imagine that we switch the position of the magnet and now we put it in the horizontal direction. Okay. So now the remnant field is going to be in a different direction because we cannot change that. It's just now the vector of the magnetization from the magnet is going to be in a different angle with respect to the direction of sensitivity of the fluxgate. So now you can see that the anomaly looks like a bipolar anomaly. You have a minimum and you have a maximum. And as you move the magnet away from the sensor, it's pretty much go back to the preliminary DC value. So the magnetic anomalies are much complicated than the ones associated with gravity because it's a combination of the geomagnetic field superposed with any ring magnetization on the objects plus the response of the object after being induced magnetization by the external geomagnetic field.